here to present quite a bit of work from quite a number of people with regards to a new undergraduate game AI research competition that had its inaugural year last year. What I'm going to do is I'm going to describe the motivation for that, the challenge problem for the inaugural event, the contest structure and results. I'm going to just briefly overview the approaches of the top 3 players and discuss their similarities and differences for this problem. So we called it this alphabet soup of a name, EAAI NSG Challenge. The EAAI stands for the Symposium on Educational Advances in Artificial Intelligence. This has been running since 2010, co-located with AAAI. The NSG is an internal joke when people say, well, what does NSG stand for? We say that the NSF has its grand challenges. Ours are not so grand. And that's not to deprecate the contest, but we know that if we're going to engage people in a relatively short time frame, we need to have a low bar for entry in terms of the complexity for modeling the problem. We need to have something with relatively simple rules, simple specifications, so that people can focus on the research and not just getting the problem modeled correctly. So the goal of this is to teach the craft of research to undergraduates. One of my favorite quotes by Sophocles is, "One must learn by doing the thing. For though you think you know it, you have no certainty until you try." And so the goal of this competition is to support and enable faculty to have high-quality undergraduate research experiences that include the full cycle. That is, not just the experimentation and the learning and the expansion of knowledge, but also the write-up, the submission, the peer review, the acceptance, rejection, and possibly the publication and presentation at a major CS conference. And so that's the grand goal of this. And the challenge problem for this first year is a game called Parameterized Poker Squares. Now, to describe that, I need to first describe Poker Squares. Poker Squares is a folk solitaire game that I've been able to trace back in the literature to 1949. Obviously, it was invented after poker and sometime probably before 49. But it makes use of a standard 52-card deck, and what you do is you shuffle the deck and you draw and commit placement of cards to a 5x5 tableau, that is a 5x5 grid of positions. Once placed, the card cannot be moved. After 25 draws and 25 placements, you have a filled 5x5 grid. Each row and column have 5 cards each, and these 5 cards are classified as they would be classified in poker according to hand type. So each hand of these 10 row and column hands that exist in the 5x5 grid is scored according to some point system. Here's an example of one of the more popular point systems. The American point system has its basis in how valuable hands are in the game of poker. So royal flush is most valuable with 100, straight flush 75, on down to one pair being 2 points, and a high card hand, this is basically none of the above, being 0 points. An example of the scoring, here's a grid, maybe difficult to see in the back, but basically looking at the 5 columns at the end of this game, we have a royal flush for 100 points. We have 3 columns that are just flushes, not royal flushes. We have a pair in this column, a pair of 6s. Going by rows, we have 2 pairs for 5 points, a pair of kings for 2. In the 3rd and 5th rows, we have full houses, 5s full of aces, 10s full of 6s, and we have 3 of a kind of 3s in the 4th row. And so all of these points in the point table get added up for a total score, in this case, of 229. And that's Poker Squares. I want to just pause for a moment and see if anyone has any questions about the basic game of poker squares. Yes?
So it looks like you don't count the diagonals?
No, no. It's purely the rows and the columns.
Just on go. What's roughly 24 factorial?
So the size of the problem, we'll get to that in a future slide. So parameterized poker squares is just started out with the observation that there are more than one point system in use. There is, competing with the American point system, there is the British point system, which is based more on the difficulty of forming the hands in the game of poker squares. So one could argue that this is a superior system, even if it shows up less in online versions of the game. But these are two different systems. And I got to thinking, well, the play is very different for these 2 point systems. And the play would be very different still for other point systems that departed even more radically than these, made a more radical departure from these. And so what I thought of was just parameterizing the scoring table so that points for any given hand classification would be from minus 128 to 127, that hands would still be classified as in the game of poker, but you could be greatly rewarded or you could be greatly penalized for a hand. So it's some example point systems. We have, as part of the contest code, a generator for what I call Ameritish point systems. These are American and British point system proportions and the space of all of the proportions that are in between, sort of, the scaled between the proportions of the American and the British point systems. There's single hand point systems. So imagine that you only award 3 of the kinds and score 0 for nothing else. Hyper corners, which means that you perhaps randomly decide that you are going to penalize or reward any given type of hand with a 1 or a -1. And random, of course, is the full range of different allowed scoring tables. So that's parameterized poker squares. It's just simply poker squares parameterized by the scoring table. So the structure of the game, of course, this is a game of chance. We have this expect-to-max tree that has alternating chance nodes where we're drawing a card and choice nodes where you're committing that card to the grid. And as far as the game tree size, you have 52 possible first card draws, followed by 25 possible placements, followed by 51, followed by, and so on and so forth. But it's actually not this bad, because we would, observe that different draw and play sequences can lead to the same state. And further, if you think about it, if you swap any pair of rows, any pair of columns, it's an equivalent game. Nothing really changes as far as your expectations. So even with symmetries and even with different paths to the same state, even if we were to figure out exactly how many there are, it's still too many to evaluate the entire tree. So it makes for a non-trivial search problem, and we can only evaluate entire expect-to-max trees when we're close to the end of the game. So the contest results, or actually the evaluation of the players, players were not told exactly which point systems they would be tested with. They were tested with 12 point systems that were generated from a random seed. And for each point system, players had 5 minutes for their programs to process the point system, to develop any kind of strategy, heuristic evaluation, etc. And then play 100 games with 30 seconds of decision time per game. Then total scores were linearly scaled for each player between 0 and 1, where 0 was given to the player with the minimum total score across the 100 games. 1 was given to the maximum total score across all games, and everything else was linearly scaled in between. In this way, you didn't have a bias towards systems that gave out more points. And so, tested on 12 different point systems. A player that, for instance, if they managed to get the maximum total score for every single point system, then they would get 1 12 times, so 12 points possible. And the result of the contest where we had 10 teams register and 7 teams follow through. You'll notice here, looking at these numbers, we have a cluster of 4 that have 11 and above, 1 in the middle, and a couple at the bottom. And so there's a pretty tight cluster of good performers here, approaching ever more closely towards 12. I'm not going to get into details on the data, but I'll just briefly mention, since the co-authors and such, the #1 team was composed of students Carol Castro-Wunsch and William Maga, with faculty Kaylin Anton of McEwen University. Second place, the team that I advised with Colin Messinger and Zhuoxi Yang from Gettysburg College. And the third place team was Team Tiger with Robert Arrington and Clay Langley, with Stephen Bogarts as their advisor from DePauw University. So on to the overviews. BMO was the #1 finisher with an average of 98.5 of the maximum possible points. So very, very strong. Made use of a parallelized flat Monte Carlo search, and the heuristic evaluation, one thing that you'll notice across my summarization here is that in the heuristic evaluation, there are a number of similarities between the top entries. There are also some differences. I'll highlight those in the conclusion slide. But the first thing is that all of these assumed row and column independence of expected partial hand scores. Now, this is an important point here, so I'm going to flesh this out a bit. In the mid-game, you might have some rows or columns that are full or empty, but you will also have ones that are in between, that have a couple of the spots filled. And you'd like to have some sort of measure of what you would expect that you would be able to score in that row or column as the game progressed. So, thing is, rows and columns are not independent from one another. If you need the same card, you can imagine, if you need the same card at this position in this column and in this position in this row in order to fulfill what you're trying to do in that row and column, then that's a dependence between the two. So if both the column and row, not at their intersection point, demand the same sort of card, that's a dependence. So this independence assumption is an abstraction that it's unfounded in the game, but it turns out to be a good assumption. And one of the things, I'll do a bit of a spoiler in advance, one of the things the teams found is that by making this abstraction and then applying Monte Carlo techniques, the dependencies came back in the search. So tossing out any kind of attention to dependence between rows and columns, that was an important thing for working a heuristic. And so assuming the row and column independence, and then working to abstract each partial hand into some form that one could then learn on, like learn expected values for. And then taking, as the heuristic evaluation, the sum of the expected scores. In the case of BMO, BMO had each partial hand encoded as a 16-bit string encoding salient features. And so BMO's heuristic evaluation encoded each of the partial hands, then did a lookup on how much was expected from each towards the final score. And since the final score is the sum of your hand scores for the 5 rows and the 5 columns, then the heuristic evaluation is simply the sum of the expected bit string scores for the grid. Those bit string scores are initially learned with Monte Carlo reinforcement learning, and BMO was parallelized in its search to maximize the use of available cores both at learning time and during play, which is to say that that BMO turned this laptop, which was the test machine, into a hair dryer for the duration of the contest, blowing out hot air like I'd never had anything to do. So that was good use of resources. The bit string itself, say the first 9 bits are indicators of whether or not certain hands have been achieved in that row or column. The 10th bit is whether or not the hand is a row hand. Now I've just said that this abstraction doesn't deal with dependencies between pairs of rows and columns, and that's still true. But in one's learning, it is important in this game to know whether you are working on building a row or building a column, because there are certain hands that work with each other and work against each other when they are orthogonal to one another. So let's take as an example something that would be in competition. Let's say that I had a pair of 3s in a row and another 3 in a column, and I wanted to get more 3s in the column and in the row. Perhaps the vertical 3 completes a full house where there's 3 of some other rank, but it would make 3 of a kind in the row. Those work against each other. Those are at odds. Similarly, suppose that I had 3 hearts in a row and 3 spades in a column, and nothing in the space intersecting the two. Then I might still believe that I have chances for a flush in both of those, but only one of those flushes can possibly win out. So good strategy for many of the point systems oftentimes consists of trying to work your rank set collection hands in one direction and your suit hands in the other direction. In other words, things like 3 of a kind, full house, 4 of a kind in your rows, as an example, without loss of generality, and in the columns to have flush, royal flush. And you can see that in the example that I gave earlier, where the flushes and in general the suit-oriented hands were vertical, and the set collection hands, the rank set collection hands, were horizontally oriented. So this bit allows the learning system to converge to its own partition of the hands naturally, where they're complementary to one another. So those are the first 10 bits. The last 6 bits, the authors describe these as being context bits. I would call them undealt card bits. So these are the bits that talk about how many cards are still undealt of the primary rank, and these are the number that are undealt of the secondary rank. And these last 2 bits, 0, 1, and 2, encode whether there are not enough cards for a flush, exactly the number of cards for a flush, or more than enough cards for a flush. So moving on, Gettysburg player here fell short by 0.5% in the overall score. So very close, and a very similar approach. The main difference is that we underutilized our resources. The student that designed the search, the one that worked best for them, only used 9% of the allotted time. This is definitely an area for improvement for this player. Instead of bit strings, we just had strings of salient features. And I'm going to skip over that encoding in the interest of time. But we also used Monte Carlo reinforcement learning, but we used epsilon greedy simulation with an exponentially decaying epsilon across our 5 minutes of learning. So this is an example of a hand abstraction where 14 cards have been dealt in the column. The column has 3 separate ranks with 3, 2, and 2 cards of those ranks left in the deck. There's still a flush possibility with 8 cards left to complete the flush from 3 cards, and a straight possibility is still there. Tiger got 3rd place, 94.5%, made use of open source Monte Carlo tree search with a very high UCB1 exploration parameter 200 times the normal one. It pruned moves with the lowest heuristic score and had a hand-tuned heuristic based on weighting partial hand patterns. So I'm unfortunately out of time to go into detail of that, so I'm just going to conclude here by saying that if you get nothing else from this, know that this is a very fun little solitaire game and a nice test bed for research. Very accessible. All the code for the contests for classifying poker hands and scoring things and setting up scoring tables is available freely online from my homepage. Although this only attracted 7 submissions in its first iteration, I consider it a modest step forward towards encouraging undergraduate game AI research. And while all of them shared in common the abstraction of the state space, in assuming they did different abstractions of the state space, yet they made the same independent assumptions about expected partial hand scores and refined decisions using different Monte Carlo techniques for each of the top 3 entries. One of the things that I conjecture, I'll finish with this, one of the things that I conjecture is that the first 2 heuristics were very on the bias variance spectrum of function approximators, had very low bias, high variance possibility as far as function approximators, whereas the 3rd place one had one that was more hand-coded, more tightly parameterized, and you could say had less bias, or had more bias, less variance than the others. And so as a result, what I took away from that is that the simpler Monte Carlo searches for this, having a lower bias heuristic function that was learned, ended up being superior to a more sophisticated UCT search that had a higher bias, more restricted learned heuristic function for this problem. And so that's all I have for you.
Okay, thank you. Perhaps you can take time for just one short question. Yes.
Your scoring system supports cases where, for example, a full house is not considered better score than a 3 of a kind.
Right. So you have a
Does
jeopardy.
that affect the results, whether this phenomenon occurs in an actual situation or not?
So very often, if you don't want to go to a rarer hand that would be more valuable, in a scoring system that penalizes a harder hand. So as a simpler example, say you have 3 of a kind, and 4 of a kind for some reason gets strongly penalized in the scoring system. Usually you can find some place to chuck that 4th card and not make the 4 of a kind. But there are situations where that is a jeopardy. And so that's one of the subtleties in strategy of play, is always the question is, where do you place that card to maximize your expected utility? You maximize your expected score. And in some cases, certain plays that you might think are the same are not, because of the way that they reduce the jeopardy of bumping up your hand classification to something that gets penalized in the scoring system. Does that answer your question?
So you would expect that if you separate these 2 categories, the one where it's always improving and the one where it can be penalized, that it would lead to quite different strategies.
Yes,
So,
different scoring systems give very different strategies.
So, and also that would separate in the overall outcome of what can be reached using Monte Carlo methods. Did you
Right,
observe that?
and this problem has a nice characteristic of having both short-range things that are easy to see in the search and evaluation, but then you need to have the Monte Carlo learning in order to have a possibility of working towards longer-term goals across the game, like getting flushes, getting straights, etc.
Okay. In the interest of time, I would like to carry on. So thank you very much.